So, welcome again to the new lecture of this course, Fundamentals and Applications of Dielectric Ceramics. So, let us just briefly recap the last lecture. So, in the last lecture we introduced tensor notation of properties. Which is important from the perspective of properties in the crystals, because the properties of materials are not isotropic. Most properties are isotropic in nature, because stress is a tensor, strain is a tensor, and basically tensors are nothing but matrices of components more than 9. Okay. So, scalar is a 0 rank tensor is defined as this formula 3 to the power n. So, for a tensor n is greater than or equal to 2, n is equal to 0 will mean scalar, and n is equal to 1 will mean it is a vector, and n is greater than or equal to 2 will mean it is a tensor. So, a tensor will have 9 or more components theoretically speaking, and as a result your stress properties such as stress, strain, modulus, they are all tensors. So, stress and strain are second rank tensors, and modulus is a fourth rank tensor. Similarly, we looked at dielectric properties. You have epsilon ij which or chi ij, which is, so this is epsilon ij is permittivity, chi ij is susceptibility. These are all both second rank tensors, and when you look at polarization in electric field, these are all vectors. So, these are second rank tensors. And so, in general you will see that the proportionality constant, the property which is the proportionality constant, whether it is susceptibility or dielectric constant or modulus or compliance, they will have a rank which is higher than the rank of the stimuli. So, if you saw in dielectric properties, the stimuli is electric field, the value that you measure is polarization, both are vectors, and the proportionality constant is susceptibility, which is a tensor. Okay. Similarly, so these are, so you can say that rank 1 tensors are polarization electric field, and accordingly the rank 2 tensor will be the proportionality constant. When you looked at the stress strain, stress and strain are rank 2 tensors, and correspondingly the proportionality constant, which is elastic compliance or stiffness, it becomes a fourth rank tensor. So, fourth rank tensor can be very tricky because you have 81 components, but life is little easy for us because of thermodynamics and crystal symmetry arguments, that we can reduce this number from 81 to 21 or even lower. So, that way we are lucky. So, we then started our discussion on piezoelectric properties. So, we did not we were not able to get into equations, but we just defined what a piezoelectric is. So, we will continue on those aspects based on crystal symmetry first, before we look at the piezoelectric properties in mathematical form. So, from, if you recall, if you look at the lecture notes in of MOOC in structure of materials, you will recall that there are something called as crystal classes, and these crystal classes are defined on the basis of 32 point groups. Okay. So, point groups basically you can say they are sort of addressed to the structure of material in some sense. Okay. So, point groups are related to space groups and so on and so forth. The space group consider the motif into consideration. So, as a result these 32 point groups become some 230 something space groups. We are not going to go into crystallography, but basically you can say 32 point groups are 32 representations of points in a space, using, considering that the distribution of points in the space is space filling and symmetric. And so, out of these 32 point groups, when you apply symmetry arguments, there are 21 which are, you can say, non-centro symmetric, and remaining 11 are centro symmetric. And what we saw in the last class is this centrosymmetric or non-centrosymmetric. Centrosymmetric will mean having a center of symmetry, which means you can replicate, if you have a center of symmetry, you can replicate a point at x, y, z to minus x, minus y, minus z. Okay. If you do not have center symmetry, then you will not be able to do this transformation. So, basically the environment at x, y, z will not be similar to environment at minus x, minus y, minus z, which means you cannot perform that symmetry operations. So, 32 point groups are based on distribution of points in space, based on symmetry arguments and so on and so forth, which you can look at in the details related to crystal structure MOOC course, a structure of materials MOOC course. So, the piezoelectric materials belong to those materials which are non-centrosymmetric. So, what are these? So, let us just define the crystal classes with respect to, so let us say we have several crystal classes, crystal system let us say, then we have centrosymmetric groups and we have non-centrosymmetric point groups, let us say PGs. Okay. So, here we write first as cubic, then we have tetragonal, then we have ortho rhombic, then we have hexagonal, and we have trigonal, which is rhombohedral, and then we have monoclinic, and we have triclinic. Among these let us say we have these point groups, cubic, tetragonal, okay. So, among these we have M3, M3M, these are non-centrosymmetric, these are centrosymmetric. Then we can say 4, this is also represented as M, 4 or MMM. Then we have MMM in orthorhombic, in hexagonal we have 6 or M as well as 6 or MMM, or then trigonal we have 3 bar and 3 bar M. We have 2 or M, and then here we have 1 bar. So, if we count the total number, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 centrosymmetric point groups. In the non-centrosymmetric point groups, we have cubic. So, we have 4, 3, 2, bar 3 M, 2, 3, then we have 4, 4 MM, bar 4, 2 M and 2, 2. In the orthorhombic we have MM2 and 2, 2, 2. In the hexagonal we have 6, 6 mm, and here we have bar 6 M2 and 6 2 2, and then we have 3 M and 3 2, 2 M and none, and 1 and none. I will tell you why have we drawn the, why we will come to a minute to the reason why we have drawn them in 2 columns in a minute. So, these are all you can see non-centrosymmetric point groups. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So, we have 21 total. Okay. I have put them in 2 columns because in the non-centrosymmetric there is a further division that some of these are polar and some of these are non-polars. So, ones on the left are polar. Polar means they have, the crystal will have a dipole moment, a permanent dipole moment, and non-polar are the ones that even though they are non-centrosymmetric, they are not polar. The crystal does not have a, the dipole moments basically you can say cancel out each other when you put in ions on them. So, you can see that in the cubic crystal there is no polar group, but in the cubic, but you have non-polar group in cubic crystal. So, you have non-centrosymmetric non-polar groups, but you do not have any polar non-centrosymmetric. So, you can see that polar is a subgroup of non-centrosymmetric. If it is centrosymmetric, it can never be polar. So, for something to be polar, it has to be non-centrosymmetric, but that is not a sufficient condition. It can be polar, there is a possibility for it to be a polar only if it is non-centrosymmetric, but it is not guaranteed that a crystal will be polar if it is non-centrosymmetric alone. As you can see that some of the non-centrosymmetric crystals are, cubic crystals are non-polar, but they are not polar, nothing is polar. Similarly, you can see in tetragonal, while 4 and 4 mm are polar, bar 4, bar 4 2m and 2 2 are non-polar, even though they are non-centrosymmetric. And similarly, we have these many other crystal systems. So, out of these we have 10 which are polar and 11 which are non-polar. So, out of these, so as far as piezoelectricity is concerned, the requirement is that crystal must be non-centro. So, even though the material is cubic, as long as it is non-centrosymmetric, it will have piezoelectricity. Okay. So, the only requirement is crystal must be non-centrosymmetric. So, it applies to all the 21 point groups except 432. So, with the exception of 432, everything else is piezoelectric. So, which means out of 21, 20 are piezoelectric. So, as long as your material belongs to these 20 point groups, it will be a piezoelectric material. So, this is a must requirement, a piezoelectric material must be non-centrosymmetric. It can be polar, it can be non-polar, it does not matter. So, basically piezoelectric properties is coupling of mechanical properties to electrical properties. And as we will see, there are direct and indirect piezoelectric effect. There are two effects that we can see, we will see them later on. So, a piezoelectric material is something which couples mechanical properties to electrical properties. Upon application of a mechanical stimuli, it shows mechanical response, electrical response, or upon application of electrical stimuli, it shows a mechanical response. But the fundamental requirement for the material is that it must be non-centrosymmetric, that is, it must lack center of symmetry. Build upon this further, we get to what we call as pyroelectric crystals. Pyroelectric crystal must be non-centrosymmetric, then it must also be polar. So, except 432, okay, except 432. So, 432 is in non-polar anyway. So, there are 10 point groups basically. So, we can remove actually this 432 because it is anyway not piezoelectric. So, it can't be pyroelectric as well. So, first requirement is it must be non-centrosymmetric, and then second requirement is it must be polar. So, there are 10 point groups on the left that we drew, all of these are all non-centrosymmetric and polar. These materials are all pyroelectric. So, pyroelectric material, what is a pyroelectric material? Which couples temperature with electrical response. So, a pyroelectric material is something by definition which is non-centrosymmetric and which must be polar, that is, which must have a polar axis, a unique, basically it means that it must have a unique polar axis, which means it must have dipole moment along that axis. Okay. So, that is what a pyroelectric material means. Then we come to third class of material, which is called as ferroelectric materials. For a ferroelectric materials, the requirement is it must be non-centrosymmetric, it must be polar, which means it must have a unique polar axis. Third requirement is the polarization along the polar axis is reversible by reversing the electric field. So let me just depict this. So for a pyroelectric, this is a pyroelectric, okay, and here we draw a ferroelectric. So for a pyroelectric, let us say this is the polarization vector, okay. So when you apply electric field in this direction, this remains in this direction, but when you apply electric field in this direction, the P remains the same, it does not affect it, okay. So when you change the electric field direction, the polarization direction does not change. In the ferroelectric crystal, when you apply electric field in this direction, your polarization is in this direction, and when you reverse the direction of electric field, the polarization also reverses. It has to happen, the polarization is reversible by reversing the direction of electric field. This is what makes it a ferroelectric. Also ferroelectrics are materials which have a transition. So the ferroelectric material will disappear above a certain temperature called as Curie temperature. So they have a ferroelectric transition, which is typically a phase transition, as we will see in the thermodynamic. At a temperature called as Tc, okay. So if you now look at it, there is all centrosymmetric materials are piezoelectric, right, which means all centrosymmetric materials, right, sorry, non-centrosymmetric materials except 432. So all my apologies, that all non-centrosymmetric materials are piezoelectric except 432. Within these non-centrosymmetric materials, you have 11 of them which are, so this is basically you can say 20 PGs, right. Within these you have 10 PGs which are polar. These are all pyroelectric. Within these we have another class which is ferroelectric, for which polarization is reversible. This number is not very well defined, so we cannot say what this number is, but basically what we can say is that every ferroelectric material is pyroelectric and piezoelectric by default. Every pyroelectric is a piezoelectric by default, but not necessarily a ferroelectric, okay. And pyroelectric material may be piezoelectric material may be pyroelectric or may be ferroelectric, but not necessarily. So this is sort of a diagram, Venn diagram kind of, you see that piezoelectric is a broader class of materials, pyroelectric is a little restricted class of materials from 20 to 10 point groups, and ferroelectric is even more restricted class of materials. So this is a basic you can say classification of piezo, pyro and ferroelectric materials. So let us get back to the properties of piezoelectric crystals now. So we were talking about the piezoelectric effect. So this introduction that I have given you, this was necessary just to differentiate between the piezo, pyro and ferro. We will come to that in a little bit more detail later on. So, piezoelectric materials are basically materials which are polarized not only by application of stress, but also by stress. Okay. So, there is a linear relationship. So, there are two kinds of effect. First is called as direct piezoelectric effect, and this direct piezoelectric effect is that dI, which is the charge density, this is related to stress xjk, and the proportionality constant is small d I j k. Okay. So, you can see that d is the basically, as we saw dielectric displacement, the charge density, right. So, this is charge density, which is nothing but polarization, right. Charge density di, this is proportional to xjk, which is the stress tensor, and the proportionality constant is piezoelectric coefficient, which is direct piezoelectric coefficient. Okay. So, this is basically, you can say this is Coulomb per meter square, this is Newton per meter square, and this will be Coulomb per meter square divided by, so this will be Coulomb per Newton. Generally the values are noted in terms of picocoulomb per Newton, but basic unit is Coulomb per Newton in the SI units. Okay. So, this is the piezoelectric coefficient, which is the direct piezoelectric coefficient. So, you can say this is direct piezoelectric coefficient dIjk, which is a third rank tensor. Okay. dIjk, because it couples stimuli of rank 2 with the measurement quantity of rank 1. Okay. So, now they also have another property which is called as indirect piezoelectric effect or converse piezoelectric effect. So, converse piezoelectric effect is that change, you have a change in dimension when under the influence of an external field. Okay. So, when you apply electric field, then they show change in the dimension or the strain. So, this converse piezoelectric is basically strain is related to electric field. So, this is described as xij, small xij, that is equal to dkij into ek, or you can say this is also written as d prime ijk into ek, and sorry, not prime, but I can say, I can write it transpose. Okay. So, T, this is the transpose of matrix, and this is basically called as converse or indirect piezoelectric coefficient. Okay. So, again you can see the units, this is unitless and this is volt per centimeter or volt per meter. So, this would be picometer per volt. So, you can see the direct piezoelectric coefficient will have a unit of picocoulomb per Newton, and in this case the units will be picometer per volt. Basically, for a volt of voltage, what is the displacement that you measure in picometers? Okay, it is a very small displacement, that is why it is typically in picometer, but you can say it is in meter per volt. Okay. So, it is very small, that is why we generally write it in terms of picometer or nanometers, things like that. So, these are two piezoelectric coefficients that we have. One is the direct piezoelectric coefficient dijk, and second is the indirect piezoelectric coefficient, which is dkij, which is transpose matrix dijk t, superscript t. Okay. The units are picometer per volt for indirect one and coulomb per Newton for the direct piezoelectric coefficient. Okay. So, there is also something about the sign. The sign of these will depend upon whether you have direct sign will be determined by you can say determined by, what will it be determined by? The sign of stimuli, right. So, what is the sign of applied? So, basically you can say stimuli, that is stress or electric field. So, you may have compressive strain, you may have tensile strain, similarly you can have charge density, which is, so polarity of electric polarity will change as you change the direction of stress also, whether compressive or tensile stress that is applied. So, now essentially in this case, if since the stress and strain are symmetrical tensors as we saw earlier, this also makes that the piezoelectric tensors are also symmetrical with respect to similar indices. So, for example, dijk will mean that it will become dikj. So, this is a symmetry argument which is applied to. So, you can do again this when you write the matrix of this dijk, and when you make those similarity with respect to what you did in the stress tensor and strain tensor, you can work out this dijk will be similar to dikj. So, this is what we have done today, and so number of piezoelectric coefficient you can see when you do that. So, for a rank 3 tensor you will have 27, right. So, 27 reduces to 18 when you apply this argument that stress and strain tensors are symmetric, and these can further be reduced to even lower components when you apply thermodynamic and crystal symmetry arguments. So, they are lowered in general, the number is much lower. What are the examples of these materials? Examples are silicon oxide, zinc oxide, PVDF, which is polyvinylidene fluoride, lead zirconate titanate, PbZrTiO3, and so on and so forth. These are all very good piezoelectric materials. Of course, among these are ferroelectric materials. So, they are necessarily piezoelectric, and these are only piezoelectric. So, for example, the quartz watches that we wear, they are based on piezoelectric effect, and in those materials silicon oxide quartz is the one which is used for piezoelectric as a piezoelectric component. So, we will stop here today, we are running out of time. So, what we have done is we have basically discussed what is the crystal basis for piezo, pyro and ferroelectric materials, and then we have looked into the tensor notations of piezoelectric properties. We will further dwell upon in the next few lectures. Thank you.